Hello everyone, welcome to the third lecture of Analog Microelectronic Circuits Unit 2. So in the first lecture of Unit 2 we have seen uh, bipolar junction transistor, its device structure, physical operation, the different modes of operation, uh, even characteristics, the three configuration and the characteristics, the common base input output cara and common emitter input and output cara. And in the second lecture we have seen various DC biasing and the DC numericals, the basic current equation, uh, the relation of IE/IC alpha beta. With that we have solved numericals to find the operating point VCE/IC with all these kind of biasing circuits. Now in today's lecture we'll look at the small signal operation and models of BJT transistor. So in the first lecture, while discussing the modes of operation, we have seen when the emitter base junction is forward biased and collector base junction is reverse biased, transistor will be in active mode, and this active mode of operation is used to amplify signals. So after DC biasing and the numericals associated to that, in today's class we'll look at the small signal operation and equivalent circuit of BJT. So let me start with a simple biasing circuit. So here this RC is the collector resistance. This is connected to VCC, and emitter is grounded. So here to the base terminal a small signal is given and a DC voltage is also given. So this DC voltage, this is base and this is emitter. This should be forward biased. So this DC voltage I mark it as VBE, and this small signal I'll give this as small v and small be. That means from base to emitter you have a composite signal which is small v capital BE. Right. Now when you apply a small signal and a DC, so even in the MOSFET discussion we have done the same thing. Always small signals or AC signals are applied on DC. So here the meaning is you have a DC bias which is VBE. On that we are applying a small signal which is VBE. So the composite signal what we have here is VBE, which is actually the sum of VBE and capital VBE. Right. Okay. So before considering this small signal, so when I do this, you will be having a current. This current is also small I capital E. This is the collector current and this is the base current. So this is the picture of a transistor which is biased on the input side using VB and output side. So this is actually the output side. Here the transistor is biased using a resistor RC from a supply VCC. So here we have a voltage called VCE. Right. So these things are there. Now let us analyze the circuit without this small signal first. So let me only consider the DC bias in the circuit, and if I consider only DC bias, the circuit will be like this. So here we have the DC voltage VBE. This is RC which is connected to VCC. Now this voltage is VCE, only DC, and this current will be only DC current. Since I'm considering only DC bias, only DC currents flow here. So in this terminal you have IE and this is the IC current. Now Yeah, so what we'll do first is, before drawing the small signal equivalent circuit, we will look at the relationship of different currents, uh, and how we'll first write the small signal currents in the circuit, then we'll develop the small signal equivalent circuit. Now, so if I look at this circuit, even in the previous lecture, I have written that collector current IC is equal to Is into e to the power of VBE by VT. Eta VT, I'm considering eta as 1. So this is the collector current. Now if collector current is this, I can write emitter current as collector current by alpha and base current as collector current by beta. Right. So these things I can write. And if I look at this collector voltage VC can be, VC is actually same as VCE because emitter is grounded, and that voltage is equal to VCC minus IC into RC. These are the currents, the DC currents in the circuit, and the voltages VC in the circuit. Now, so after understanding the DC bias and the conditions, now we'll consider if a signal is applied to the circuit. The same VBE signal is applied to the circuit, then the composite signal VBE is equal to DC bias plus small v BE. This is the signal. So since we have a DC voltage and an AC voltage, and this is the composite signal, I can write the composite current here. So I capital C is equal to Is into e to the power of VBE by VT. So what we are doing here is, we are just looking at the relationships of DC currents and AC currents, right? Okay, so IC equal to Is into this quantity, or this can be further written as Is into VB can be written as capital VB plus small vb, so e to the power of VBE plus VBE by VT. So this can be further written as Is into e to the power of VBE by VT into e to the power of VBE by VT. So this is IC. Now if I look at this quantity, Is into e to the power of VBE by VT, that is same as the DC collector current. So that means I can write IC equal to DC collector current into e to the power of VBE by VT. Now, so we know that this VBE is a small signal, and if I do a small signal approximation, that is assuming that this VBE is very small, maybe it is less than some 10 millivolt, we call this a small signal approximation. Why I am considering it as 10 millivolt is, the VT voltage, VT is actually the volt equivalent of temperature, and room temperature it is 26 millivolt. Now if the VBE is very less compared to VT, or if it is less than 10 millivolt, I can do a small approximation here. E to the power of x can be written as 1 plus x if x is very less, right? So in that way I can write IC equal to IC into 1 plus VBE by VT. Can write in this way. So e to the power of minus 1 plus x if x is very small. That is idea. Okay, so now this can be further written as IC equal to IC plus IC by VT into VBE. IC by VT into VBE. Now if I look at this composite signal, so this is the composite current. Now this is the DC current. That means this should be the AC current. That means so I will use I capital C for composite and I C this for AC current, just to differentiate. So from this I can write I small c, which is a small signal current, is IC by Vt into VBE. IC by Vt into VBE. Now if I look at the graph, if I look at IC VBE, which is the composite signal VBE, and the IC graph, basically VB is the input voltage and IC is the output current. So VB is the input voltage and IC is the output current. So these two will be related by, or IC by VB can be conductance. Since it is input and output, we call it as transconductance. So this can be written as GM, or this GM can be equal to IC by VT. That means collector current is equal to GM times input voltage, VB voltage. IC equal to GM into VB, where I define GM, the transconductance, as IC by VT, where IC is the collector current, DC collector current, and VT is the volt equivalent of temperature. Right. So this is one very important thing. Now if I look at the graph, input voltage VBE and output current IC, it will be something like this. Now for a DC VBE, say this is the DC VBE. On that DC VBE, we will be applying a very small signal, which is your VBE. So for this DC VBE, we will get a current that we call it as collector, that is a DC collector current. Now for this variation, for this VB variation, we will get a varying collector current here. This variation we'll get, right? So the important thing here is the transconductance of a transistor, of a BJT, can be written as IC by VT. And second thing is the collector current can be written as GM into VBE, right? Yeah, so this is very important. Now when we compare this with MOSFET, so we have the same relations in MOSFET. MOSFET, it is ID equal to GM into VGS, and there your GM, there are several relations for GM. Mu and Cox under root value, that is a 2ID by VOV is also that, right? So these are the MOSFET relations. Now in contrast to MOSFET, so in MOSFET we know that input impedance is infinity, or the impedance looking at gate is infinity. Impedance looking at emitter is 1 by GM, right? And impedance looking at source is 1 by GM, and impedance looking at drain is R0 if source is grounded, right? So these things we have seen. Now we'll try to understand the input impedance for BJT, because in the MOSFET configuration, if your input is given to gate, always input impedance is infinity. But in your this case, in BJT case, that is not true. So there will be some finite input impedance if the input is given to base, because there is a base current. So that we'll do first. So we'll look at base current and input resistance seen at base and base, which is very important, which is not there in a MOSFET, because in MOSFET gate, the equivalent thing is gate current is 0, so gate resistance or the input resistance at gate is actually infinity. So I'm just continuing with the previous expression. See, don't worry about all these expressions. This is very, I started with the simple diode equation here. From diode equation I actually developed all the equations, so you can also write all these things and get the final small signal current, collector current IC as GMVB and GM as IC by VT. These relations will be useful when you solve numericals. Yeah. Now, if I know collector current, composite collector current, I can write the composite base current IB. IB can be written as the collector current divided by beta, IC by beta. Now what is this composite collector current that I have written here? Composite collector current is approximated and written as this. So I'll use the same form, same thing, I'll take it over there. So this can be written as IC plus IC by VT into VBE, the whole divided by beta. Now IB is actually the DC base current plus the small signal base current IB. Now if I compare this, this gives that DC base current is IC by beta, which we know. So if I can write the small signal base current, which is IC by VT into VBE divided by beta. Now what is IC by VT? IC by VT is GM, that we have seen here. IC by VT is GM, so this is GM. So IB can be written as GM into VBE by beta. GM by beta into VBE. So this is base current. Now so this is the transistor and I am looking at base. Now the small signal input resistance, between base and emitter, looking into base. So I can find the impedance looking into base as well as looking into emitter. So looking into base is, so how to find that? So the signal is here, so I want to find the impedance looking into base. So this is the base. Now here the voltage is VBE and the current here is IB. So if I want to find the resistance, to know the resistance, I'll write that resistance as VBE by IB. So VBE by IB can be directly written from this expression. VBE by IB is actually beta by GM. VBE by IB is beta by GM. And this resistance, the small signal input resistance between base and emitter looking into base, is called as R pi. The resistance is named as R pi. So R pi, the base resistance, the resistance looking into base is written as beta by GM. R pi is beta by GM. Now if R pi is beta by GM, I can further simplify this by substituting for beta and GM. So how can I do that? R pi is beta by GM. So beta can be written as IC IC equal to beta IB. So I'll keep this beta, and GM is IC divided by VT. Now for beta I will write IC by IB. So IC by IB divided by IC by VT. That means R pi is equal to VT by IB. So there is another small signal parameter, the small signal input resistance looking into base R pi, which is equal to VT by IB. Similarly, in a similar way, I can write the small signal resistance at the emitter side as well. So before that I will write emitter current and input resistance at emitter. Emitter current and input resistance at emitter. In a similar way I can write how I have written for base. In a very similar way I can write the same thing for emitter as well. So let's see how to do that. So emitter current IE can be written as IC by alpha, right? Here I have written IB as IC by beta. Similarly I can write IE as IC by alpha. That means it is equal to the DC current by alpha plus the small signal current by alpha. So this IE can be written as DC emitter current plus small signal emitter current. So I know that small signal emitter current is small signal collector current by alpha. And what is a small signal collector current? That we have written here also. Small signal collector current is IC by VT into VB. So I'll write it as IC by VT into VBE, which is small signal collector current. So when I write IE here, all these are small signal collector current. So IC. So when I write IE here, which is equal to IC by VT into VBE by alpha, right? Now what is IC by alpha? So I know that IC equal to alpha IE. So what is IC by alpha? I can write it as IE. So IC by alpha is IE by VT into VBE. Now what we are looking here is the small signal resistance looking into emitter. That means if I am looking into emitter terminal, that means base should be common. I am looking at emitter terminal, so plus minus VBE, and the current here is IE. So looking into emitter to find the resistance, that resistance should be VBE by IE. So what is VBE by IE? Which is equal to VT by IE in this case, and we call that resistance looking into emitter as RE. RE is the resistance looking into emitter. So this is also important. So to summarize the expressions what we have done now, one is the small signal parameter, which is the transconductance, is IC by VT. Second is R pi, the base resistance that we obtain here, which is VT by IB. And third is RE, the resistance looking into emitter. This is R pi is resistance looking into base, which is RE is VT by IE. Right. So These relations are very important. Now let us find one more relation from all these. So GM and RE relations we know. So by combining these two, by combining GM is IC by VT and RE is VT by IE. So if I combine these two, I can get another relation, which is IC by GM can be equated to RE into IE, or I can get alpha IE by GM is equal to RE into IE. If I cancel these two, I can write alpha equal to GM into RE, or RE equal to alpha by GM. Now alpha is a quantity which is very close to 1, so I can approximate this as 1 by GM, which is a very useful relation. So what I obtain here is RE equal to alpha by GM, which is approximated as 1 by GM. Now if you remember, in the case of MOSFET, the resistance seen from source is equal to 1 by GM. Similarly, now in the case of BJT, the resistance looking into emitter is actually RE, right? So what we obtain here is RE is approximately equal to 1 by GM. So for MOSFET and BJT, the resistance looking into emitter or source are same, are equal. 1 by GM is equal to RE. This is very important. Now one more thing related to the resistance looking into the relation between the resistance looking into base and emitter. Relation between RE and R pi. So both are defined. Both resistance are defined, right? Now if you look at this, I can say VBE is equal to, it can be written as IB into R pi, and from the second thing, from the second relation, I can write VBE as IE into RE, right? So if I equate these two, IB into R pi is equal to IE into RE, or can write IB into R pi is equal to IE is IB into beta plus 1 into RE. That means R pi is equal to beta plus 1 into RE. So this is also another very important relation, R pi equal to beta plus 1 into RE. Right. So just to remember, if this is VBE and this current is IB, the resistance seen from here is R pi, which is the resistance looking into base. Resistance looking into base. Similarly, now if this is VBE and this is IE, the resistance looking into emitter is RE. Now this RE and R, so this is actually the resistance looking into emitter. Looking into emitter. RE and R pi both are related with this expression. Now so with this idea, so what we have done here is we started with considering a circuit which is having a small signal as well as DC. First we have written the DC expressions, then by considering the small signal applied, considering the composite signal, arrived at the transconductance first, then we have written the base current and the input resistance seen at base, which is R pi, and also emitter current and the input resistance seen at emitter, which is Re, and the relation between Re and R pi. So now with all these discussion, we can directly draw the equivalent circuit of BJT. So when I draw the equivalent circuit of BJT, first I will draw for common base configuration. So why I need to draw two different things is because when I apply input to base, the resistance seen is R pi, but when I apply input to emitter, the resistance seen is Re. Because of the input impedance difference, I may need to draw these two things. So if it is common base, so considering this as base, this is base, this is emitter, and this is collector. So the current direction, the small signal current IE is this direction, this is IB, and this is IC. So conventionally I'll consider this as emitter terminal, this as collector terminal, and here I have the base terminal. So with the discussion what we have done now, we can straightforward we can draw the equivalent circuit. The resistance seen between emitter and base. So there is a for resistance seen between emitter and base. Why? Yeah, that question also we should answer. Why there is a resistance? Because emitter base junction is forward biased. When it is forward biased, it is having the characteristics of a diode, and for this diode you have so this can be best represented using a resistance because you have a dynamic resistance or AC resistance. Now the resistance between emitter and base is equal to, I can write this as Re, because the resistance seen into the emitter is written as Re. Now the current direction is IE is this, that means base current should be in this direction and collector current should actually flow in this direction. This is the current. Now I can write this as a controlled current source. Now if I look at the output characteristics of a BJT in common base mode, you can see that IC versus VCB, you can see that we discussed this in the previous lecture, we have discussed this. You can see IC almost equal to alpha IE. That means you have a controlled current source. So I'll mark this as alpha into IE. Alpha into IE is the controlled current source. So this is for the common base. For the common base. Now the same thing I can draw for common emitter. So what is the difference? For common emitter, so this is common emitter, right? So I need to draw the resistance seen into base. So here I will draw base, this is emitter terminal, and here I have collector terminal. Now between base and emitter I have a resistance. Resistance seen into base is R pi. R pi is actually equal to beta plus 1 into Re. We call it as R pi. Now here again, if you look at the common emitter characteristics, this is VCE versus IC. You can see that again your collector current is equal to beta times input current IB, but you can see actually a slope. The slope is accounted by the phenomena called base width modulation that we'll discuss shortly. So anyway, even the transistor collector current also act as a control current source. Now emitter current is flowing in this direction, so this is base current IB. So collector current is this direction and its value is beta into IB, because collector current IC is related to input current as beta into IB. So this is the small signal model of BJT, both in common base and common emitter configuration. So we have two different models because of the base current, the presence of base current in contrast with the MOSFET. Now, so in these two models, so this model is known as RE model because we are representing transistor in terms of resistance looking into emitter. So we call this model as RE model, and the model which uses the resistance looking into base, we call it as Hybridpi model. Hybridpi model. So this is known as RE model, and the other one is Hybridpi model. So in this Hybridpi model, we include the input resistance looking into the base, that is Rpi. So here actually we can represent this in another way too, so that I'll show you here. So in the Hybridpi model, pi model basically because of the resistance Rpi. So here the resistance is Rpi, and here it is showing a control current source beta IB. So this is emitter, this is base, and this is collector. Now this beta IB, so the idea is to represent MOSFET as a voltage control current source. I can do that, voltage control current source. So here MOSFET is represented using a current control current source. The same thing I am just changing by representing it as a voltage control current source. To do that, so beta IB can be written as what is beta? If you remember, we have obtained the expression for beta. Beta is Gm into Rpi. Beta is Gm into Rpi. So I'll use that Gm into Rpi multiplied by this. IB can be written as, IB is this current. So IB is the, so sorry, I forgot to mark the voltage here. So this should be marked plus minus. This should be marked VBE. Now yeah, so I can write this as, this is VBE. So IB can be written as VBE divided by Rpi. So this means beta IB is equal to Gm into VBE. So if I draw an equivalent circuit by considering this is Rpi, this is VBE, this is a base terminal, this is the base current flowing inside. Here the control source can be represented by voltage control current source whose value is Gm into VBE. So this is emitter IE, and this is the collector current IC. So these are two slightly different versions of simplified Hybridpi model for the transistors, right? So to summarize all these things, so we have written certain small signal parameters. One is Gm, which is IC by Vt. Then we have written Rpi, the resistance looking into base. Rpi resistance is written as Vt by Ib. Then we have written the resistance looking into emitter, which is Vt by IE. That we have written Vt by IE. Then the relation between Rpi and Re. Rpi is beta plus 1 into Re. Then we have observed one more thing, which is the relation between GM and RE. So RE is alpha by GM, or approximately 1 by GM. And finally, we have replaced the control current source with the control voltage source. So I'll just draw the equivalent circuits also. This is one equivalent circuit, alpha IE, where I have RE. This is known as RE model, VBE. This is IB. Now this is RE model, and the Hybridpi model. So this is VBE, this is RPi, this is base current, this is beta into IB, collector current. The same beta IB can be replaced using GMVBE. So this is a controlled current source, current control current source, and this is a voltage control current source. So this is a summary of the discussions what we have done so far. Now let's use the concept what we learned to solve certain numericals. Let us start. Okay, before that, let us see how these equivalent circuits can be used to design, like used to analyze an amplifier circuit. Now in this case, so this is your common base thing, and this is your common emitter, and generally common emitter resist. So we also connect a resistance R0 here, which we call it as the same. We have used an R0 resistance in the case of MOSFET because of the finite output resistance. Similarly, initially when I have drawn the models, I assume that the output impedance is infinity, but that is not true. Especially in common emitter characteristics, you can see a slope, and that accounts for this R0 resistance. Right. Maybe before solving a numerical, we'll see that common emitter cara. So if I look at this characteristics, so this is VBE and this is VCE. Now if I look at the output characteristics of this VCE versus IC, so IC is related to the input current is IB here, so IC is beta times IB. So even though IB is very small, you can we will get a large IC because of this beta times IB value. So you can see an increase in current there. Now at this same graph we have developed actually in the previous lecture. Now for smaller values of VC, at low values of VC, at low values, of VC, or I'll state that if VC goes less than VB by some 0.4 voltage, the same thing, because what I am looking here is this VCB voltage. VCB is the junction the collector base junction should be reverse bias. So if VC goes less than VB by 0.4, what will happen to the collector base junction? That will turn forward bias, and if that happens, transistor will leave active region, or transistor will go to saturation. If transistor go to saturation, collector current will not be there because there is no voltage to sweep the electrons reaching the base junction, right? So that means at a given VBE, if VCE, this voltage, increases, so after this will drop. Now at a given VBE, if VC increases, what will happen? So if VC decreases, the transistor will move away from active, it will fall into saturation and the current drops. Now if VC increases, what can happen here is this junction will be more reverse biased, right? If VC increases, reverse bias of collector base junction will increase. Now what will happen if reverse bias between this collector base junction increases? See, this is base and this is collector. This is base and this is collector. If reverse bias increases, whenever a junction is reverse bias, there will be depletion region. Now if the reverse bias increases, depletion region will actually widen. Now this widening of depletion region will actually affect the base region because base is very thin, right? So reverse bias of the collector base junction will increase. That will in turn reduce the effective base width. This will in turn reduce the effective base width. Now one thing I am stating here, we will not look into the details of that. The saturation current IS, which we write in the diode equation, is inversely proportional to the width of the region. Now what will happen if the base width reduces? If base width reduces, this IS will increase. So if W reduces, IS will increase. If IS increases, IC also increases, because IC equal to IS into e to the power of VBE by VT. Now if IS increases, IC increases, right? So if IC increases, that increase in IC is actually shown in this graph, this portion. So what is actually happening here? As we increase VCE, the reverse bias of this junction increases. When the reverse bias increases, naturally the depletion region width increases, and that depletion region width will affect the base region because base is very thin. As a result, effective base width will reduce. Now since width is reducing, effective base width is reducing, the saturation current will increase. That will in turn increase the collector current. That is what you can see. There is an increase in the collector current, right? So this phenomena is called as base width modulation, because the width of the base is actually changing here. We call this as base width modulation. A similar phenomena we have seen in MOSFET, which is channel length modulation. This is observed by a scientist called J. Early, and this effect is also known as Early effect. So what we have done in MOSFET, the same thing we will do here as well. If we extrapolate this line, this current, this will meet in this x-axis, and we call this voltage as early voltage, right? Now to account for this, generally we write IC as IS into e to the power of VBE by VT. Now if you remember, in MOSFET we wrote ID as ID sat into 1 plus lambda into VDS, where this lambda is 1 by VA, right? Or I can write this as VDS by VA. Similarly, we will write here IC as IS into e to the power of VBE by VT into 1 plus VCE by VA. 1 plus VCE by VA, where this VA is the early voltage. VA is the early voltage. So why I explained this is, in common emitter configuration, we can see actually this slope, the finite output resistance, and this is in fact accounted in the small signal model by considering R0. So this R0 is actually the effect of base width modulation in a common emitter configuration, right? Okay, now we'll quickly see uh, how to how to apply this small signal equivalent circuit in certain numericals. Okay, so let's look at this question where you have a transistor So this is only a part of a circuit. Given that this resistance is 800 ohms, also given that emitter current given that emitter current is 0.18 milliamps and beta equal to 49. So we are asked to find the resistance seen here, input resistance, and also the resistance seen from this side, which is output resistance. You can consider this node as a common node. You can consider it as a reference point, or you can consider it is connected to ground. So we are asked to find the input resistance and output resistance of this circuit. So when I say input and output resistance, definitely the question is small signal input resistance and small signal output resistance. So we have to use equivalent circuit, small signal equivalent circuit. So for that we need to find small signal parameters also. Okay, so I'll explain how to solve these kind of problems. First of all, see whether in which equivalent circuit we can use for this. So here what I can see is the input, for the input impedance thing, we are looking into the base. So we can use we have two models. We have discussed two models. One is common base model, another is common emitter model. So in this circuit, this is actually common emitter configuration, but you have a resistance connected to the emitter node. This is same something called as common emitter with a degeneration resistance. Same thing. We'll discuss this a little later. Now input is given to base and output is taken from this side. So the suitable model what I can use here is, since it is in a common emitter configuration, common emitter mode, I'll use the input is to the base. So I have to write R pi here, and here I can write beta into IB. This is the model. Common emitter model is what I am using. So this is the equivalent circuit of transistor. Only that part is done. Now emitter side I'll leave it as such. Collector side, we have no idea about the collector side, so we'll leave it as it is. Now at the emitter side we have a resistance connected. That resistance is 800 ohms. Right. Now yeah, this is connected to some DC potential. So that at the equivalent circuit we'll just ground it. Now the first thing is we need to find both input and output resistance. So the transistor is replaced by the equivalent model R-pi, or I can write this as beta plus 1 into Re. Anything I can write. And here there is a resistance. So the first thing is to find input resistance R in. Right. So before, so to find input resistance, what I should do is I should connect a test voltage. So let me mark the currents here. This is IE and this is IB. So I should connect a test voltage here. V test. The current is I test, but the I test current is same as IB. So to find Rin can be written as V test by I test, or I can write V test as IB into beta plus 1 into Re. So V test is the voltage from this node to ground. That is a drop across this resistance beta plus 1 into Re, which is IB into beta plus 1 into Re, plus the drop across the resistance 800 ohm, which is the current flowing through, that is IE. So I can write this as IE into 800 ohms. So as of now I'll just mark it as a resistance Re to get an expression. Now IE is related to IB as the same thing, beta plus 1. So I can write this V test as IB into beta plus 1 into Re plus Re. So V test by I test, which is same as IB, equal to beta plus 1 into Re plus Re. Right. Now for this particular problem, beta is given as 49. To find Re is Vt by IE. IE is given. Vt is 26 milli by IE is 0.18 milli. That will give you Re of 200, almost 200 ohms. So your input resistance Rin is beta is 49. So 50 into 200 plus Re. Re is 800. Is equal to 1000 into 50. So it is 50 kilo ohm is the input impedance by applying the small signal equivalent circuit. Similarly, to find the output impedance, what I should do if I want to find the output impedance, the input side should be shorted. Same thing. So I'll use the same equivalent circuit, which is beta plus 1 into Re, and this is beta IB. This is the resistance of 800 ohms. So that's to find the impedance from this side. This is ground. On this side, the voltage is VB. This is the equivalent circuit. Now since I am finding output impedance, I am actually shorting this to ground. Now I want to find the impedance from this side, right? So this is IB and this current is IE. So if you remember, since I want to find the impedance looking at this terminal, I can write the output resistance as 800 ohm parallel to the resistance seen at that terminal. So I'll mark it as Rout dash. So I'll since 800 ohm is connected in parallel to the resistance seen from this side, I'll keep 800 ohms aside to connect a test voltage here, find the impedance, find the resistance, and finally it will be combined or connected in parallel to the 800 ohm resistance. So what I will do is I will keep this aside and I will connect a test voltage here, V test, current is I test, Yeah, you can so both things are same, right? So what I will do is, these two resistors are connected in parallel. So what I have here is, yeah, so to find the output impedance here, the simplest way is to keep this aside and see the impedance seen from this side. So now, without solving only, actually you can tell the impedance seen at this side. So what is the impedance seen from emitter? Yeah, so that we have derived little before. So the impedance seen from the emitter is actually, if it is MOSFET, the impedance seen is 1 by GM. So here it is equal to RE. So what is the output resistance? Output resistance is 800 ohms parallel to RE. What is RE in this case? RE we obtained as 200. So it is 800 parallel to 200. 160 ohm is the output impedance. So it's directly, I'm applying the small signal equivalent circuit. I'll just explain this once again. This was the equivalent circuit what we had. This is 800, and you are asked to find the impedance from this side. So to find the impedance from this side, I am just keeping 800 ohms separate and finding the impedance looking into the emitter. So I know that the impedance looking into the emitter is equal to RE. So that RE will come in parallel to 800. So your output impedance is equal to 160 ohms. Right. Okay. Now, yeah, if I want to, yeah, we will see one more numerical. With the common base thing. The question is, find the incremental resistance between points A and B, given beta equals 99 and R naught equal to infinity. So this is the question. So with this we'll wind up, and we'll continue in the next lecture. This is given as 1 milliamps. This is 0.5 kilo ohms. This is A and this is B. It has to find the incremental resistance, that is a small signal resistance seen between A and B. Now, if you look at the equivalent circuit, we'll use the RE model because this is a common base thing. So in equivalent circuit, this is actually a current source. This will remain open. If I replace transistor with its equivalent, this is RE, and here I have alpha into IE. This is for the transistor. Given that R0 is infinity, so no need to consider any output impedance here, but you have a 0.5k resistance here, which is connected to this point. Yeah, this is the equivalent circuit. Now you are supposed to find the impedance between points A and B. That means I'll actually connect a test voltage V test here, which will in turn give I test here. I test is same as IE. This is IB. Sorry, this is the current direction is the other way. You have a PNP transistor. So this is IC. So how to find the impedance seen from this side, right? So I know that V test by I test is the resistance what we need to find, resistance between points A and B. So how to write V test? V test is equal to voltage between this point and this point. That means drop across RE plus drop across 0.5K. Drop across RB can be written as IE into RE plus drop across 5K is 0.5K into IB. Right, which is equal to, I'll write in term for IE I'll write I test. So I test into RE plus, how IB and I test are related? IB equal to IE by beta plus 1, where IE is I test. So I can write this as 0.5K into IE by beta plus 1, where IE is same as I test. So V test by I test is equal to RE plus 0.5K divided by beta plus 1. So what is RE? What is RE? RE is equal to VT by IE. IE is given. IE is given as, yeah. So IC is given as 1 milliamps. Beta as 99. So I can find IE from the alpha, which will be approximately 1 milli. So I'll consider this as 1 milli. So 26 milli by 1 milli is equal to 26 ohms. RE is 26 ohms. So the resistance seen is equal to 26 plus 0.5K divided by 100, which is equal to 31 ohms. Right, yeah. So try to understand the equivalent circuit of transistor RE model and RPi model properly, and then solve these two problems, which will give you confidence to solve any resistance calculation. So we'll continue amplifier analysis in next class. Thank you.